Hello, my name is Nikolay Vereshchagin. I am from Moscow State University and from HSE University and from Yandex. I will start with a well-known definition of the class NP. Informally, NP languages are those for which there is an efficient proof-checking procedure. Efficiency means here that the length of the proof is bounded by a polynomial of the length of the input, and also the time needed to check the proof is bounded by a polynomial. Formally, we say that L, a language L, is in the class NP if there is a Turing machine V, whose inputs are binary strings X and Y, which works in time bounded by a polynomial in the length of X and has the following property. For all strings L, X is in L if and only if there is a Y such that V on the input X and Y outputs 1. Here V is understood as a proof checker. It outputs 1 if Y is a valid proof of the membership of X and L and 0 otherwise. Note that the length of Y must be bounded by a polynomial in the length of X, because otherwise we just can't read Y. In this context, Y is called sometimes a certificate or a proof or evidence. We will need also the generalization of this definition, in which we allow V to be probabilistic polynomial time machine. This generalization is called the class MA, Merlin-Arthur class. We will regard probabilistic machines as deterministic machines with auxiliary random input Y, Z. And so in the formal definition of the class MA, we fix some parameter epsilon, which is a constant strictly less than 1/2. And we say that X, that a language L is in MA if there is a Turing machine V with 3 inputs X, Y, and Z. X is the input, Y is the candidate proof, and Z is the randomness needed to the proof checker V with the following properties. If X belongs to L, then there is a valid proof, which means that it is accepted with probability larger than 1 minus epsilon. And if X is outside L, then all the proofs are invalid. That means that the probability that they are accepted is less than epsilon. So why this class is called Merlin-Arthur class? Because we consider here the following scenario. We understand the proof checker as a king, as a fictitious hero, King Arthur, and Merlin is a wizard in the court of King Arthur. And Merlin wants to convince Arthur that certain strings are in the language. And to this end, Arthur has a polynomial time machines V, which is used to check the proofs. And the requirements ensure that if X is indeed in L, then Merlin can find the proof for that, which convinces Arthur that X is in L with probability close to 1. And if X is outside L, then whatever proof is provided by Merlin, it will be rejected with probability less than epsilon. So the second line means that Merlin can't cheat Arthur. So formally, this class depends on epsilon, and so we use the subscript epsilon. But actually, one can prove that it doesn't, as long as epsilon is strictly less than 1/2. And here it is important that the inequality is strict. So in what follows, we will drop the subscript epsilon. We will need also another generalization of the class NP, which is the simplest version of probabilistically of interactive proofs. So the class is called now Arthur Merlin because we formally will just switch the quantifiers in the definition of MA. So what does it mean? We say, we fix epsilon, and we say that ln which L is in the class AM, if there is a Turing machine V, again with 3 inputs, again polynomial time bounded, with the following property that if X is an L, then with probability more than 1 minus epsilon, there is a proof which is accepted with that randomness. And if X is not in L, then the probability of the very same event is less than epsilon. So what's the difference? The difference is that we switched the order of quantifiers. So the quantifiers over Y is now after the quantifier over Z. So what does it mean? That means that now Merlin can adapt his proof to the randomness because he now knows the randomness. So if we just take the very same probabilistic proof checker V and switch from Merlin Arthur protocol to Arthur Merlin protocol, then the task of Merlin becomes simpler. If X is in L, then Merlin can choose the very same Y and use it for all Z, not adapting into Z. However, now he can cheat because if X is not in L, he can adapt Y to Z, and so he can increase the probability of acceptance, and from being less than epsilon, it can become close to 1. So that's the difference between two versions of Merlin, between Arthur Merlin and Merlin Arthur protocols. And again, one can show that this class doesn't depend on epsilon, and so we can drop the subscript. Both classes generalize NP, and an interesting question is whether this is they are indeed superclasses of NP in the sense that they are different from NP. And this question is open. Both questions are open, and usually one can formulate them whether we can de-randomize MA or de-randomize AM. And it turned out that both questions are very hard because one can show that they can't be resolved via relativizable techniques. What does it mean? Most theorems of complexity theorem are valid even if we replace all the definitions, all the machines in the definition of complexity classes by machines having access to any fixed oracle A. Such theorems are called relativizable theorems. And so Baker, Gill, and Solovey showed that there is an oracle under which P space is equal to P. That means that all the classes between P and P space are identical. All of them coincide with P. And all the classes I have considered so far are indeed between P and P space, and so they all coincide. And that means that using relativizable technique, we can't obtain negative answers to both of the above questions. On the other hand, the folklore theorem shows that there is another oracle under which AM and MA differ from NP. That means that also positive answers to our questions can't be proven by relativizable technique. That means that both questions are hard. What is the relation between these two classes, MA and AM? It turns out that MA is a subset of AM, meaning that interactive proofs provide a more powerful device than just probabilistically checkable proofs. A more detailed version of this theorem reads as follows. Let's restrict in the definition of our protocols the amount of randomness using by proof checkers by sampling normal A of the length of the input, and also the length of the proof by sampling normal M of the input. And let's denote the resulting class by MA of little ma. And so it turns out that this class is a subset of AM, where the length of the proof is again M, but the number of random bits is larger by a factor of order M. Which means that in the transformation of MA protocols to AM protocols, the amount of randomness increases by a factor of M. Why is this? So the usual proof is as follows. The definitions of MA and AM are similar. The difference is also only in the order of quantifiers. So when transforming, why it is we cannot prove the theorem just by considering the same verifier. So assume that we have a verifier for MA protocols called V. Then we know that if X is null, then there is a proof accepted with probability 1 minus epsilon or larger. Let's take the same verifier and consider now it for Arthur Merlin protocol. And it seems that it is clear that the task of Merlin becomes even simpler because he can use the same proof for all these. But on the other hand, if X is not an L, then we know by definition that all the proofs are rejected with high probability in our Merlin-Arthur protocol. But the probability over Z that there is a proof that is accepted with that Z might increase drastically because this is the probability of the union of these events over all Y's. Every event has a small probability less than epsilon, but by union bound, the probability of their union is the sum of, is at most the sum of probabilities, and that sum can be much larger than epsilon. In the first case, it is epsilon times the number of events, that is the same epsilon times 2 to the m. And so such a transformation works only if the probability epsilon times 2 to the m is smaller, say, than 1/3. That means that if we consider MA protocols where the number or the amount, the probability of error is exponentially small, that means less than 2 to the minus m times 1/3, say, then in the transformations or in the transformation of MA protocols to AM protocols, we do not need to change the proof checker. And it turns out that such a transformation and so to use this idea, we need to make the probability of error exponentially small. And this can be done using the standard amplification. The standard amplification allows to decrease the probability of error from any constant strictly less than 1/2 to exponentially small, to say 4 to the minus m, at the expense of increasing the amount of randomness by a factor of order m. And this is done as follows. We take our procedure V to check the proof, and we apply it, we run it several times on the same inputs, but with different z's. And we take order m different z's, all of them independent of each other. And then we take the majority vote. We accept the proof if the proof is accepted in the more than 1/2 of trials. And by Chernoff bounds, the probability of error tends to 0 with exponential rate as m tends to infinity. As a corollary, we obtain that for every language in MA with parenthesis little m little a, we can choose some polynomial time verifier whose probability of error is less than 4 minus m of the length of x. And the amount of randomness it needs will be order of MA. And that proves our inclusion. Actually, one can do much better using amplification via expanders. So Alon, Feige, Wigderson, and Zuckerman showed that one can decrease the probability of error from constant to exponentially small at the expense of increasing the amount of randomness from A to A plus order m and not A times order m. And this is done using expanders. So we consider random strings as nodes of an expander of constant degree, who has 2 to the m, 2 to the a nodes. And instead of running m times on independent z's, we take only one z at random using a random bits. And then we start a random walk from that z. And we run our proof checker on all the intermediate nodes. That means that we use intermediate nodes as randomness for the proof checker. And again, we take the majority vote. And the amount of randomness is A plus m times the number of bits needed to to specify a neighbor of each node. And this is constant because the degree of our expander is constant. And one can show that indeed the probability of error decreases exponentially, although we use dependent random strings. As a corollary, we obtain that the class MA with parameters little m, little a is a subset of AM, where the amount of randomness is now a plus order m, and the length of the proof is the same. So Alexander Knop asked whether we can improve this inclusion even further. More precisely, he conjectured that there is some polynomial P such that in the transformation of MA protocols to AM protocols, the amount of randomness is bounded by a polynomial which depends only on A, on the initial amount of randomness, so that we can get rid of M at all. Formally, there is polynomial P such that MA of MA is a subset of MA, where the length of the proof can be arbitrary polynomial, and the amount of randomness is P of that polynomial A. Actually, Knop conjectured a little bit different things, which we will call the full version of his conjecture. And that full version reads the same, but instead of normal MA and AM, we use heuristic their version. Heuristic means that the protocols might err on a small fraction of input strings. So this conjecture is interesting because of its connection to the circuit complexity. One can show that the full version of the conjecture implies that for all constant k's, there is a language in NP whose circuit complexity grows as n to the k, where n is the length of the input. Note that at the current time, we can't show even that for k equal to 2, there is such a language. And so this conjecture is very interesting. And on the other hand, it is very implausible. So can we refute Knop's conjecture? And it turns out that we can't do it using relativizable technique. It's very hard to do it because of the following theorem by Gach, Sipser, and Lauteman. They showed that if P equals to NP, then all the classes MA, IM, and P are identical. And hence, we do not need randomness at all in the definition of MA and AM protocols. And so the Knop's conjecture holds. And this theorem has the following corollary. To refute the conjecture, we first have to prove that P is different from NP, which is very difficult with the current technique, as everybody knows. And so one can now ask whether we can prove the conjecture, not refute it. And our main result shows that this is very implausible conjecture, and so it's very hard to prove it. And we can show that we can't prove it using the relativizable technique. More precisely, there is an oracle under which, for all polynomials P, we have that the class MA where the length of the proof is P of n plus n, and the length of amount of randomness is A of n, for some A, which is actually equal to n, is different from AM, where the amount of randomness is P of A of n. Which means that we have separated MA with which refutes Knopf's conjecture. And moreover, we can also refute the full version of Knopf's conjecture, and even more. Under that very same oracle, the class MA with the same parameters is not included in the heuristic version of the class of MA with P of n. So the second inequality refutes both simplified version of Knopf's conjecture and its full version. And actually, our results hold even in a stronger form. Consider the class AM with parameter 1/2. As I have said, this class is probably much larger than AM. And still, one can show that there is an oracle under which, for all polynomials, we have that the class MA with parameters P of n plus n and n is not included in the class AM with parameter 1/2, where the amount of randomness is P of n. And because this holds for all the polynomials, it refutes Knopf simplified version of Knopf's conjecture even in a more strong way. And also the second, the analog of the second theorem works also in this strong form. So thanks for watching.